Okay, good morning, everyone. It's my pleasure to be here to introduce the theory and the first result from the Large Binocular Telescope. First of all, I would like to thank the following people over there for sharing slides with me. So this is a picture of the LBT, the two-telescope instrument, which is located in Arizona. And the LBTI is the instrument that combines the light from the two telescopes. And it's really like a Swiss knife. It has a lot of options. So you can, for instance, combine the two lights on the same detector, but separate the two beams and do regular AO imaging. So we had a lot of theory about that already. Or you can overlap the two beams on top of each other and do interferometry or NRM imaging. John Monnier has talked about that yesterday. Or you can combine the two beams on top of each other in phase opposition and do nulling interferometry. And I'll talk about that in this talk. For the science, the LBTI covers a wide range of science topics, but we have mainly two surveys. The first big survey that we are doing right now is a planet survey. It's called LEACH. It's using an L-band camera in the LBTI, and there is an exozody survey. So I won't talk about the planet survey in this talk. So this is a nice image taken by the LBTI, and in this case, we did not overlap the two beams on top of each other. We took two separated high contrast imaging of this system. So I'll talk about the exozody. Jean-Charles just introduced the modeling of debris disk. I won't talk about that. Tomorrow, Mark Wyatt will introduce the evolution of exozodies. I won't talk about that, but I will explain to you how we can detect exozody with the LBTI. Okay, and before I really start, I'd like to show this slide from Chris Univ. So I was sitting in the audience about, I think, 8 years ago. I was a novice in interferometry, and he had that slide here saying that interferometry is like any new skill, like walking. You have to want to learn, because it's not always really intuitive, interferometry. At the beginning, you crawl, and then you walk, and eventually you will run. So you should assume nothing here. If you have questions, please ask them. I'm here to answer your questions. So this is the outline of my talk. I will start by introduce the theory of nulling interferometry, how does it work, and then I will explain what it is for, the science motivations behind it. Next, I will introduce the concept of the LBTI, the instrumental specificities, the main science goals, and the first results. And I'll end this talk with a quiz, a really short quiz. So first of all, how does it work, nulling interferometry? First question you should ask yourself is, what is light? It's maybe a simple question for all of you, but it was not so obvious a few centuries ago. So in 1704, Newton came with his corpuscular theory of light, and he said light, in fact, is a stream of particles because it travels in straight line at high speed. And you can predict the path of the light because it's a stream of particles. But then in 1802, Young came and he said, no. Light is a wave because it's diffracted and it undergoes interference. And he had this now famous double-slit experiment. So if you have a source and the wavefront is going through two slits here, and then you look at the screen, if light was really a stream of particles, you would see behind each spot, you would expect to see a spot of light behind each spot. But this is not what we see. What we see is many spots. And due to the theory of wave, you can predict actually the spacing between the spots. I'll come back to that later. But there is an analogy, really quickly, short movie, showing an analogy of that, of a wave at the surface of water. So if you have one wave, you have one slit, you have concentric waves going out of it. And then if you had a second source, you start to see this pattern now where you have constructive and destructive interference. So I took this movie I just discovered this YouTube channel a few weeks ago, Veritasium. It's really interesting, a lot of short movie about science stuff. You can look at this movie here. There is a movie about the double-check experiment. So now if we have two objects, two sources, if the two objects are overlapped, same image on the screen, but then if you have a slight offset between the two objects, you will start to see two fringe patterns will be offset with respect to one another. And this will decrease the contrast of your fringes. And you can use this information to infer the geometry of your source. So at some point, for a given angle here, alpha, the two set of fringes will be completely out of phase. And you won't see any fringes. The contrast will be 0. And if it's the case, there is a simple formula here saying that for 0, the angle is related to the wavelength and the baseline. So you can use the baseline, which is the distance between the two slits, and you can infer something about your object here. You can infer the angular size of the object. And when we have no fringes here, we say that the object is resolved. So a two-element interferometer is based on this principle. So the idea is to have two distant telescopes. We call the distance between the two the baseline. And what you do is you sample a wavefront, two different locations, here and here. And then the idea is that you have the light from each has to be coherent for the combination. So what you have to do is to introduce in one arm of the instrument here, you have to introduce a delay line to compensate for the delay, the external delay, which is here on this arm. You have to compensate for that in order to do the interferometric combination. Come back to that. Oops. There we go. So a nulling interferometer is based on the same principle, but in one arm you have a pi phase shift here. And you do that in order to create a destructive interference on the line of sight. So if you have the two waves, one here and one from one side here, from the other side there, you introduce a pi phase shift, and then you will add the two, and you'll have destructive interference. So let me go back to the key ideas. Maybe it's really simple for everyone, but quickly. So light behaves sometimes as a particle, a stream of particles, sometimes as a wave. The wave behavior of light is at the basis of the interferometric combination. A few critical functions of any interferometer are the sampling of the wavefront at different locations. We have to match the optical path of the different beams, and combination and detection. And for a nulling interferometer, it's the same principle. There is an extra phase delay, pi phase delay in one arm. And the idea is we want to create a destructive interference on the line of sight. So the output of a two-element nulling interferometer, so really quickly, this is the phase, the light, the analytical expression of the light collected on one side. You can see the phase introduced here. S times D is the geometric delay here. D1 is the small delay in your instrument. And then you have the expression of the light at your second telescope here, where you have the D2, which is the long delay here that you introduce to match the geometric delay, and you have the pi phase shift. So at the combination here, what you do is you add the two waves together. And what you detect actually is a time average intensity. So what you have to do is to take the sum of the two, do the average, and the complex product of the two. If you do some math, what you'll get here is 1 minus cosinus kd, where k is the wave number, 2 pi over lambda, and d is given by this expression. So SB is the geometric delay, and d1 minus d2 is your internal delay. So if you match your internal delay with your external delay, what you'll get is 1 minus 1, and you'll get a destructive interference on your line of sight. So this is the intensity that you measure as a function of d, this number here. And so if d, for instance, is different by 1 lambda, then you'll get to constructive interference. And it's the same problem for your on-sky distribution. Any point in your sky plane will have a slightly different delay at your telescope. So if we call alpha the azimuthal angle in your sky plane and theta the radial distance from the star in your sky plane, you can measure the geometric delay due to the position of the object in the sky. And if you map that on the entire sky, you'll get this expression, which is called the transmission map of the Nuller. So what it is, it's really like a photon sieve. It's a sieve that you put on the sky, and everything that goes through the maximum of the transmission map will be transmitted at the output of your Nuller, and everything will go through a minimum of your transmission map will not be transmitted. And the idea is to put the star on a minimum, and then you hope to see a disk or a planet going through maximum. It's really, the basic idea is really like do a coronographic suppression of the starlight. So the key ideas too, so the output of an interferometer is a time average quantity. It has a sinusoidal response, and these are the fringes. The fringes, the spacing between your fringes depends on this parameter, KD, which itself depends on the wave number, which is 2 pi over lambda, the baseline. The larger the baseline, the higher the modulation of your fringes. The pointing direction, this is the transmission map. And of course, the optical path difference between the two arms. So usually what interferometers are trying to do is to match really well the optical path between the different arms and trying to stabilize the system to have a stable destructive interference or constructive interference. Bit of history and science motivations for nulling interferometry. So the first idea was proposed in 1978 by Bracewell, and the idea was to detect a non-solar planet with a rotating instrument. So if you have here the transmission map of a 2-telescope instrument, you have a small planet here, and you have a disk, for instance. If you rotate your instrument, the planet will go through the minimum and maximums of the transmission map, and you have a modulated signal. On the other hand, anything which is symmetric, centrosymmetric, will be constant. And the idea behind that was we can use this technique to resolve a really close-in object and to detect its presence by demodulating the signal of the Nuller. The first implementation on sky was done in 1998 at the MMT in Arizona. This is a picture of the telescope. And this is the first result here. So this is the image when we overlap the two beams on top of each other. No interference in this case. This is the image you've got of a star. Now if we overlap the two beams in phase opposition, you don't see the star anymore. And the null measurement is the peak in the null image compared to the peak value in the constructive image. And they measure for this calibrator object a null of 4%. Then they went to a science object, alpha Rho in this case, and they did the same thing. They measure the overlap of the two beams, the flux in the overlap image, compared to the flux when we combine the beam in phase opposition. And in this case, the flux, this null measurement was much higher, 18%. And with this measurement, they inferred the presence of a dust disk around this object. Next example of nulling interferometer is the Keck Nuller. It was the first 4-beam nulling instrument. So it's only 2 telescopes, but each pupil was divided in 2. And the idea behind that was to be a technological demonstrator for future ambitious space-based multi-telescope arrays. And also the science goal of this project was to measure the prevalence of exozodiacal light. I'll come back to that in a few minutes. There you go again. So this is an example of a project that was called Darwin TPFI. That was a project to detect Earth-like planet from the space with a 4-telescope Nuller. Just to show you, in this case, since you have 4 telescopes, the transmission map is more complex, and it's more complex to demodulate your signal in this case. So now let's go to the large binocular telescope interferometer. The concept of the instrument. This is a picture of the LBT. It's located on Mount Graham in Arizona. It's built and operated by partners in the US, Italy, and Germany. This is an inside view of the telescope. It's really impressive. So each telescope here is 8.4 meters. So the LBT has three key parameters. So the resolution. So you have the distance side to side, edge to edge here is 22.7 meters. So if you combine the two telescopes together, you have the resolution equivalent of a telescope which has a diameter of 22.7 meters. The high contrast, so it's an extreme AO deformable secondary mirror, which provides really high straight ratios, more than 90% at L band. And then the sensitivity, if you compute the collecting power of the two telescopes, it's equivalent to a single dish telescope of 11.8 meters in diameter. The LBTI is this green structure in the middle. It combines the light from the two telescopes. This is a front view of the LBTI. This is Phil Hinz, the PI of the project. This is the NASA sticker, meaning that it's funded by NASA. I will explain why later. So the light is coming from either side here, going to this beam combiner, which is cryogenic. And then it goes down here to this blue box, which is called NIC, and it contains different cameras for planet imaging and nulling interferometry. So this is the cartoon of the light path through the LBTI. The light is coming from either side. Here, first the visible light is reflected to the wavefront sensors on either side. The infrared light is going through the UBC here, and then goes down to the NIC camera box, which contains 3 cameras. So first, the 3 to 5 micron light is going through LMIRCam, which is the camera used for the planet survey. And the near-infrared and N-band light goes through the Nuller. The near-infrared light is used to measure the phase delay between the two telescopes. So it does that really quickly at 1 kilohertz. It measures the phase delay due to the atmospheric variations really quickly and send correction in real time to this mirror here, which is moving in piston to compensate for that. And the null measurements are done with NOMIC here. So characteristics of the two cameras. So LMIRCam is going from 2.9 to 5.1 micron. NOMIC is going from 8 to 14 micron. And the sensitivity, this is the goal sensitivity. We are not there yet for NOMIC, is to be able to detect 2 Jupiter masses planets around nearby stars with LMIRCam, and to go down to the sensitivity of 1 Zodi disk with NOMIC. And the resolution we have when we combine the two telescopes together is 0.4 AU at 10 parsec at L band, and it's 1 AU at 10 parsec with the NOMIC camera. So this is 40 milliarc seconds and 100 milliarc seconds. Instrumental specificities. So the LBT is a common mount interferometer. So usually when you have an interferometer, you point to a star, you are doing this. But with the LBTI, you move first the telescope and then you do this. So there is no external geometric delay here, meaning that there is no complicated delay line. We have only small delay lines, a few microns, to compensate for the geometric delay. And the other key parameters also is the deformable secondary mirrors, which requires really few warm optics. So this is a sketch of a classical, typical AO system. This is the LBT AO system, much less optics, meaning that we have a really good sensitivity in the thermal infrared. So the interferometric combination with the LBTI, as I said, there are many options. So we can not do interferometry at all, separate the two beams on the same camera and do regular AO imaging. We can do coronography, we can do piezo and NRM imaging. We can do dispersed interferometry, we have many grisms, or we can do nulling interferometry. And unlike most nulling instruments, the LBTI nuller is a direct imager. So we have an image on the detector. So how does it work? This is a source. There is the star here. There is a small, I'm not sure everybody can see it, but there is a small planet there. And then the idea is that you have, when you combine the light in phase opposition, you have this transmission map. So first of all, you multiply, the idea is that you multiply your sky brightness with this transmission map. This will reduce strongly the planet, the star in the line of sight, and you will better see the planet. This will improve the contrast. And then when you have done that, it's like any other imaging instrument. You have to convolve the resulting image, so source times the transmission map, by the PSF of your telescope, single aperture PSF. And what you get is this. So at the beginning, the star was really bright, the planet really faint. In the end, you don't subtract perfectly your star because the instrument is not perfect and the star is not point-like, but you better see the planet. So this is the image which is formed on the LBTI camera. So key idea 3 about the LBTI. It has 2 large apertures. They are on the same mount, meaning that we don't have any long delay line. And we have a deformable secondary mirrors, meaning that we have very few optics and a really good sensitivity. LBTI has many options, so we can do single aperture AO imaging, interferometry, piezointerferometry, nulling interferometry, and it's a direct imager. It's different. The keck is different. The keck we measure the intensity on a few pixels. With the LBTI, we really form an image on the detector. The main science goal of the LBTI. So this is the solar system in context. So as I said, we have 2 surveys going on. We have a survey to detect giant planets in the outer planetary systems. The survey is called LEACH. I won't talk about that. I will focus on debris disk. And the survey is called HOST. And the goal is to measure the amount of dust in the inner planetary systems. So zodiacal light. This is a nice picture taken from the ground here. It's dust located in the solar system, which is roughly between Mercury and Mars, and it's in the ecliptic plane. You can see here the distribution of the flux of the zodiacal light. It's a function of the ecliptic latitude, mainly in the ecliptic plane. This is a nice picture from Paranal here. And so NASA funded the LBTI to look for this dust. But why? Because it's a noise. It's a source of noise and a confusion for future direct imaging mission. So this is a model observation with a PIA coronagraph from space. And this is a Sun-Earth system at 10 parsec. If the disk, the zodiacal disk around this system is only 1 zodi, so equivalent to the one in the solar system, this is what you could see with a coronagraph from space. We can see the planet here really clearly. Now if we go to 10 zodi, so 10 times the brightness of the zodiacal dust in the solar system, it's already more difficult to see the planet. And then if we do the same thing, but if we incline the disk, I think it's 60 degrees here, for 1 zodi we can still see the planet, but then for 10 zodi already, the planet is gone. Very hard to see. And for phase-on system, this is a phase-on system with a 50 zodi disk. In this case, we don't even see the planet here, and we have to try to subtract the symmetric part of the image to detect any asymmetry. And when we do that, this is what we have. And this is not the planet. The planet is here, and this is a clump. So there is a clump following the planet on its orbit. And if the disk is as bright as 50 zodi in this case, you'll see first the clump. So we want to characterize the level of dust around nearby stars, and we want to throw away stars which have really bright zodiacal light for future exo-Earth imaging instrument. Same problem for a nulling instrument. If you have a clump in the disk and then you rotate your instrument, the clamp will be modulated at the same frequency as the planet, and you won't be able to tell anything about that. So what do we know about exozycal light? Not very much so far. So single dish photometric measurement from space, Spitzer-Weiss have shown that about 1% of the main sequence stars have an exozycal disk, but with the sensitivity of 1,000 Zodi. So we only see the really, really bright systems. To push down the detection limit, there are several surveys with interferometric instrument. There is a survey, 2 surveys with a near-infrared instruments with Chara, which is just on the hill here, and VLTI Pioneer. Steve Hertel has a poster about that, if you're interested. There was also observations with VLTI MIDI, and most recently, the Keck has just released the result of their survey, saying that it's the most precise measurement so far of exozodi, saying that with a high confidence, the mean level of dust around nearby main sequence star is probably below 60 Zodis. I want to talk about that. Okay, so the LBTI has been funded to do a survey, which is called HOST, Hunt for Observable Signatures of Terrestrial Planetary Systems. We plan to do 59 survey starting in 2015, and as I said, the goal is to reduce the risk for future EXORES imaging missions. And there was a competitively selected science team that has defined a catalog, a list of stars that we will observe. There is 2 posters about that. Raphaël Milangabe can talk about that in more details. So this is the exozodi in context. So you can see here detection limits for the different instruments, temperature on the x-axis, the luminosity, or the Zodi on the y-axis. You can see the LBTI. The goal of the LBTI is to fill this parameter space here. So we want to improve on the performance of Spitzer and Keck and go down to 10 Zodi per object. This is the goal. So the key IDs, so the exozycal light is a source of noise and confusion. So if one day one of you has a nice image of a solar system and see something that looks like a planet, but if you know that there is a zodiacal disk around the same system, you should remember my talk and think about the possibility of this marginal detection being maybe a clamp from the exozodi. I guess you have to do spectroscopy to be sure in this case. And one of the main goals of the LBTI is to determine the prevalence of exozodi around nearby objects. The first results, so we got the first fringes on sky in 2010. These are the fringes here. So just a few weeks after the LBTI was put on the telescope. This is the API team telescope. And then we obtained really recently the first closed loop measurements. So the first time we stabilized the path length variation between the 2 telescopes. That was in last December. So before last December, this is the null histogram we had generally. So this is the null measurement, this is the number of occurrence, and you see that the null measurement was going back and forth between 0 and 100%. It was following the random fluctuation of the atmosphere. But then if we close the phase loop, we stabilize the path length between the 2 telescopes. And in this case, we have a peak at a few percent in this case. That was the first measurement. I have a movie showing that. Okay, so this is a short movie illustrating that. So this is the null measurement as a function of time. The null measurement is going back and forth between 0 and 100%. You can see the star here, the overlapped beams from the 2 telescopes. Here it's fluctuating. And then when we turn the phase loop on, the null measurement is really concentrated around a few percent here. And you can barely see the 2 the two beams on top of each other. The first result, we obtained a first science result with the Nuller in February of this year around the star eta CRV. So this is the measurements here. It's a function of time. The null measurements. The blue points are the calibrator measurements. So your instrument is not perfect. You have to measure the instrumental response of your instrument. This is why we use calibrator stars. And then the red points are the science object, eta CRV in this case. And there is a clear excess in this case on top of the instrumental null. And using this information, this is a slide from Grant Kennedy, using this information, using the fact that we know the total flux from the star and the disk by Spitzer, it's roughly 20%, and assuming that the disk, the zodiacal disk, has the same orientation that the outer disk that has been measured by Herschel, we can infer the position of the zodiacal dust. So this is a graph showing the disk radius here and the disk width. And we have shown that the dust is roughly around 0.7 AU right at the inner edge of the habitable zone. So as I said, the disk around eta CRV is bright, 20% of the star, of the flux of the star. And we only see 4% because most of the flux is cancelled by the transmission map of the Nuller. So this is a representation of the flux of the disk, and you can see that in this case here, for one of our measurement, a lot of the flux is falling in the dark fringes of the transmission map. So right now we have a null depth, so of how well we can subtract the two beam of 1%, and the stability is 0.3 to 0.6%. So this is for 1 point. Now if we do many measurements, we can repeat that with a stability of 0.2%. And the goal of the survey is to go to 0.01%. So we have still a factor of 10 to 20 to go. So the goal, 0.01%, is a noise floor of 3 zodies. So this is where we are roughly right now, between the Keck measurement and the LBTI measurement. We are midway, I would say, between the two. LBTI goal. Okay, so about different results, nothing to do with nulling interferometry. This is physo imaging now. We obtained this nice image of the moon Io. So if you look at Io with a single aperture of the LBT, so the resolution of 8.4 meter telescope, this is what you would see. So the Io is here. This bright spot is a volcano on Io. And then what we did, we obtained measurement where we combine the two telescopes together and to reach the high resolution of the instrument. And if we do that, this is what we get. This is a high resolution measurement of Io. Now we can see a lot of spots on the surface. These are volcanoes. So all these volcanoes were known before. We identified 15 volcanoes in this case. They were known. But a lot of interesting things came out of the analysis of the flux from these volcanoes. Okay, another result, nothing to do with interferometry in this case, but it's about debris disk. So we obtain nice images of two debris disk systems, the blue needle. Debbie just talked about it here. So single aperture observation here, and HD, what's the name? HD 32297 here. So two agent disk, really high sensitivity images from the ground with the LBTI. Okay, so I'll summarize what I've presented today. So the LBTI is a really flexible and versatile instrument. It has many modes. We can do regular AO imaging with the redundancy of the two telescopes. We can do physo-interferometry, nulling interferometry. Nulling interferometry is used to get the higher angular resolution and at the same time to improve the contrast by destructive interference of the starlight. The exodiacal emission is a big problem. It's a source of noise and confusion for future characterization Earth-like planet. And this is one of the main goals of the LBTI, to look for this dust and find the brightest one. So I'll end up with this short question here to see if you have followed what I just said. So if you have this object here, let's say it's a binary system, you look at it with the LBTI Nuller, and you have your baseline is oriented in this direction, what would you see on the detector? Anyone? So if the two stars were point-like, they will be perfectly suppressed by the transmission map. So you would see nothing on the detector. But if the two stars are not point-like, if they are extended, a part of the light will be transmitted. So it's a multiplication with the transmission map, and then it's regular imaging, a convolution with your single aperture PSF. So this is what you would see. And that's it. Thank you. The question was, if we have a correlation between the presence of dust and the presence of planets, if we reject all the system with a lot of dust, we will reject a lot of system with planets. And that's true. But we don't know about that. It's an open question. I mean, maybe Jean-Charles or Marc can reply, but I don't think that we know already if there is a correlation between the planets and the zodiacal light.